We are Team 24035. My name is Megan. I'm an aerospace engineering major and I am the team lead.
Hi, my name is Morgan. I am an aerospace engineering major and I'm our team's procurement and CFD lead.
I'm Sydney. I'm a mechanical engineering major and I'm the FEA lead.
I'm Marguerite. I'm majoring in aerospace engineering and I'm the manufacturing lead.
My name is Eric B. I'm an aerospace engineering major and I am our wind tunnel testing lead.
Within a Honeywell turbofan engine, the compressor inlet guide vane, or IGV, is intended to regulate the airflow and pressure of the compressor. This is done by pivoting the IGV to vary its angle of attack based upon the engine operating conditions. The shape and angle of attack of the IGV creates flow separation and wake defects downstream. This interrupts the flow into the compressor, decreasing overall efficiency and impacting the mechanical integrity of the rotors. In order to address these problems, our team designed an additively manufactured compressor inlet guide vane with fluidic separation control. To achieve this, we used computer-aided design software, or CAD, to create an aerodynamic shape called an airfoil that had similar aerodynamic properties to an IGV and allowed for the injection of pressurized flow into the primary flow over the airfoil. In order to assist in the design and verify the parameters of the design, finite element analysis, or FEA, and computational fluid dynamics, or CFD, analyses were performed.
To achieve maximum efficiency, the following functional and system requirements were set. The major system requirements are that the minimal separation on the boundary layer shall be demonstrated. FEA shall indicate a factor of safety greater than 5, and the secondary flow system shall be able to inject high pressure flow that is 0 to 3% of the total air supply at a pressure ratio of 2 and with minimal leaking.
The initial stage of development involved designing a secondary flow system consisting of a base plate, a secondary flow connector, vinyl tubing, a flow meter, and a pressure gauge. The base plate design featured strategically positioned holes for securing the airfoil and facilitating accurate angle adjustments, along with notches denoting angles of attack from -4 to 20 degrees at 2-degree intervals. The secondary flow connector, an additively manufactured component, served to interface the base plate with the secondary flow system, ensuring efficient delivery of airflow into the airfoil. The minimum viable product 1 focused on testing the secondary flow system for leaks and verifying pressure and flow rate requirements. Through testing and calculation, MVP1 successfully met system requirements, ensuring effective high-pressure air optimization with minimal secondary airflow supply. The testing process involved the application of soapy water to detect leaks, verification of pressure using a flow meter with an attached pressure gauge, and assessment of flow rate and pressure ratio to optimize high-pressure air delivery.
Once it was determined that the secondary flow system could deliver the needed flow to the airfoil, we began airfoil design. We used SolidWorks to plot a Clark Y14 airfoil for a base and then completed a few trade studies to iterate the design. After filling out a Pew diagram, it was decided that the design used should have the flow exiting parallel to the airfoil surface, a small internal cavity, and holes for the flow to exit.
The next step in the design process was determining the injection point for secondary flow. The separation point is the ideal location for flow injection, as it will delay separation and the flow over the airfoil will move in the direction of the injected flow. Aerospace engineering students take a class called AME 401, where we found the pressure over a similar Clark Y14 airfoil. Using the data from this lab, it was seen that flow separates most at 60% of the chord length.
To refine the injection location along the chord and finalize the airfoil design, CFD analysis was used. FlightStream, a surface vorticity flow solver, can accurately model flow fields for models of varying complexities. A simplified model was imported into FlightStream with high-pressure flow injection points. Various injection configurations were tested, altering the quantity and distribution of holes. Optimal performance was observed with 8 holes spaced 1 inch apart, positioned at 60% of the chord, effectively reducing and preventing flow separation at the trailing edge as anticipated.
For the airfoil's initial design, testing for MVP2 occurred, with the goal of verifying the direction the flow was exiting. In order to do this, we glued tufts on the airfoil next to the holes and injected air into the cavity. A successful pass for MVP2 would be if the yarn was blown back onto the profile of the airfoil as seen in this video.
We required that FEA demonstrate that the airfoil be able to withstand greater than 5 times the testing load to ensure it wouldn't fracture inside the test section. SolidWorks was used to determine the maximum stresses on the airfoil and the minimum factor of safety. In SolidWorks, we ran a static analysis applying pressure loading to the internal cavity, hole walls, and the external surface of the airfoil. The minimum factor of safety of 8.5 exceeded the system requirement.
Once the initial design decisions were completed, we used PLA prototypes to help iterate our design process. We began with printing 3-inch prototypes to be used with MVP2, as well as prototypes of the final design. This process allowed us to determine the best way to interface the airfoil with the base plate after seeing issue with older designs. A small prototype was also made using metal, which revealed problems during printing that were communicated to our manufacturer and resolved in the final manufacturing process.
We originally planned to print our piece at the University of Arizona, but due to complications, the U of A manufacturer was unable to meet our timeline. Therefore, we printed our airfoil at ASU Polytech with Cameron No. He used a selective laser melting, or SLM 3D printer, to make our airfoil out of stainless steel 316L. SLM is an additive manufacturing technique where a high-density focused laser beam will selectively scan a powder bed to melt and solidify layers that are stacked to create a functional model. Due to the high precision and wide array of usable materials, SLM printing is ideal for aerospace applications. The printing process can be seen in these videos provided by Cameron. Since Cameron did not have a printer tall enough to print the airfoil in one 9-inch part, we sliced the airfoil into 4 2.25-inch sections. This resulted in the final design having 2 long dowels connecting all 4 sections at the leading edge and trailing edge using lock nuts to secure them together.
The final airfoil was tested in the University of Arizona Educational Wind Tunnel. Safety measures were taken by wearing safety glasses and regularly ensuring all pressurized components were clamped securely. The testing setup can be seen here. We ran tests over various angles of attack and injection pressures ranging from 0 to 40 psig. To run the test, the wind tunnel was set at the velocity of 19.3 meters per second, the same as in the AME 401 lab. Then, the shop air valve was opened to inject flow through the secondary flow system until the desired pressure in the cavity was reached. Data was then collected using a pressure transducer connected to the pitot rake in the LabVIEW DSA software.
The process data can be seen in the following graphs. The pressure deficit in the graphs is the region of the wake. A reduction of the wake can be seen at all injection pressures. The best reduction can be seen at 15 psi due to the reduction of the wake without introducing excessive pressure. Lower angles of attack demonstrated significant reduction in the wake with increasing injection pressure. At higher angles of attack, the wakes were larger and the injected flow was less effective in mitigating the wake. As the pressure within the cavity increased, we saw a greater reduction in the wake. These findings showcase the efficiency of injection in reducing the wake across various angles of attack.
Throughout the project, we learned several valuable lessons and overcame various problems. The decision to switch manufacturers for the final print came with the unexpected consequence of separating the airfoil into multiple parts. This provided valuable insights into assembly complexities and potential areas for improvement in future iterations. Exploring methods to print the airfoil in one piece could enhance structural integrity and simplify assembly, potentially improving performance and efficiency. We also had issues with data collection and identifying the problem due to a lack of familiarity with LabVIEW. We consulted the manual for the transducer and communicated with experienced personnel to identify and resolve the issue. Additionally, the project provided various insights that would be beneficial in advancing the project. Given more time, conducting tests at higher speeds would provide valuable insights into the performance of the airfoil under more extreme conditions to further validate the design's effectiveness in minimizing the wake across a wide range of operating conditions. Integrating pressure sensors along the suction surface can provide essential data on pressure distribution, further facilitating the refinement of the design.